Good morning, ladies and gentlemen. My name is Matteo Dall'Amico, and I'm here to present our experience in water flow predictions in rivers using in situ and satellite data. When we talk about discharge prediction, it's always important to specify the lead time of the forecast. So on the timeline, we can have a very short-term forecast for the next hours, or short-term forecast for the next days, seasonal forecast for the next months, and long-term projections for the next years. The recipe for producing the forecast is given by input data and the technology, and the algorithm. So the input data can be numerical weather prediction, geomorphology, in-situ data, and also satellite data. The algorithm comprise physical models, machine learning, downscaling, or other more sophisticated methods. Look at the short-term forecast. In this example, the lead time was 3 to 5 days. The aggregation was hourly, and the objective was to predict the production of a hydropower plant. The basin was located in Guatemala and had a size of around 200 square kilometers. To solve this problem, we used a hybrid approach, that is a mix of physical models and machine learning. The physical model was receiving an input, the geomorphology and numerical weather forecast, and was giving a first tentative discharge forecast. This was given to the machine learning algorithm together with historical production, and this algorithm was capable to produce a forecast of production for the next days. To evaluate the performance of the model, we used the prediction from the hybrid compared with another predictor, that is the production of the previous 2 days. In the plot you can see in green the production of the previous 2 days, and in blue the prediction with the hybrid model, and in orange the measured production. As a metric for comparing, we use the root mean square error. And in this case, you can see that the machine learning or the hybrid algorithm is providing, let's say, a decreased error compared with the baseline prediction, so the prediction of the previous 2 days. For instance, for the first 24 hours, the error decreases from 21 to 15.8. Let's have now a look at the seasonal forecast, where the lead time is up to 6 months, the temporal resolution is monthly, and the target is the discharge. In this case, we use not only in-situ data and numerical weather predictions, but also satellite data. The general modeling scheme was still a hybrid approach, where we have two components, a downscaling and also a physical model, and both components are giving data to a machine learning algorithm that is producing the forecast. For the temperature, the downscaling algorithm was based on a machine learning that was designed to eliminate the bias due to the altitude and the local microclimate. For the precipitation, the downscaling algorithm was designed to force the numerical model to comply in terms of a yearly accumulation with the measurement at the local station. In order to improve the accuracy of the prediction, we have used the satellite data to correct the estimation of snow water equivalent given by the physical model. In a sense, we used Sentinel-1 and Sentinel-2 to have an idea of the snow-covered area at a given date, and this helped us to improve the initial condition of the snow mass to be given to the model. In this case, to evaluate the performance of the model, we use the MASE, that is the ratio of the mean absolute error of the forecast and the baseline, where the baseline is the climatic average. MASE being minor than 1 means that the forecast is performing better than the baseline. And you can see that the performance is always better than the baseline, and the best performance is achieved in the spring months, just thanks to the improved information given by the snow. So we can conclude that the use of satellite data can provide useful information to improve the accuracy of discharge. Thank you for your attention.